Hi. The last video we talked about a walk that I had with my wife in the woods and how we came up with a function that related our position with our time. S of t was equal to 8t cubed, and amazingly we were able to come up with this new function which we called the velocity as a function of time that turned out to be 24t squared, that gave us how fast we were going. This is kind of one of the first amazing things you're going to find out about what calculus can do. So today I'm just going to go into a more general aspect of derivatives. So in general, what we're going to be talking about is a rate of change of one dependent variable which yesterday was our position, or S. But in general, we think of maybe a dependent variable to be y, or f of x, and it's going to be with respect to one independent variable, which yesterday was time, or t, but in general we might say x is our variable. So we're going to be talking about the rate of change, like yesterday was the rate of change of position with respect to time, and that was how fast we were going, which we called velocity. We're going to find, and it's hard not to think about the future, but we're going to be finding so many more things other than just being able to find velocity with rates of change. It's just such an important concept in our world. So the first thing we could do is just take some point, say from A to B. So if we're on the function y equals f of x, we're going from the point A, f of A, to the point B, f of B. And we could first talk about one type of rate of change, an average. And I'm just going to go rate of change. And it's going to be the rate of change of y with respect to x. So what is the change in y? Well, the change in y is that distance there. You're going from f of a is your y value to f of b. So this is the change in y. And it's f of b minus f of a. So I could write f of b minus f of a. That's the change in y. And then I can divide that by the change in x. The change in x is going to be from here to here. So that's going to be b minus a. This would be called the change in the x variable. So that would just be b minus a. You could also write delta y over delta x if you wanted to. So that's how you find average rate of change. And that's also going to be just the rise over the run, or the slope of that line. And that line has actually got a name. It's called the secant line. Don't worry too much about the terminology. Just try to understand the ideas. Now, where calculus really comes into play is now when we're looking for the instantaneous rate of change. How fast does y change with respect to x right at a point? Like say right here. what we want is the slope of this green line instead of the slope of this dotted black line. Actually, this has actually got a name too. It's called the tangent line. So what we're going to be looking for then is the instantaneous rate of change. Now, how are we going to do that? How am I going to make this slope become this slope? Well, what I have to do is maybe keep moving this point along here. Because I think as you see it, if I move this point closer, that dotted line gets closer to that slope. If I bring it even closer, the dotted line gets close to the slope of the tangent line that we're looking for. So the way I can make it come exactly to this point is I can call this point A, and this point A plus some distance h. And now the slope of that dotted line is going to be f of A plus h. Instead of f of b, it's going to be f of A plus h minus f of A all over h. But then what we're going to have to do is we're going to have to take the limit as h approaches 0. So that's going to be the instantaneous rate of change. And because that's also called the derivative, we're going to call it f prime of A. So this is actually a pretty important formula. This one also is important, but not quite as important. So we have the instantaneous rate of change and the average rate of change. Both of these are just going to give you numbers. They're going to give you the slope of the line. Now, if you really wanted to have a whole function that gave you the slope at every point, not just at point A, the only thing we really would have to do is instead of calling this A, call it x. And then this would be called x plus h. So the only difference in here, this would be called the limit as h approaches 0 of f of x plus h minus f of x. And it's still going to be over h. And now we could call that f prime of x. It's no longer just a number, now it's a whole function of x. And it'll give us the slope at every point. So that's going to be a super important formula right there. This is the derivative function. And just for terminology, if a derivative does exist, remember derivatives are limits. So limits can exist or limits cannot exist. So if a derivative exists, if there really is a slope of the function at a point, then we say it's differentiable. So if f prime of A exists, we say f is differentiable. It's a big long word at x equals a. And again, I wouldn't worry too much about memorizing that word right now. It'll be a word we use quite often during the year, and you'll get used to it. So anyway, and you're also going to find out that most functions are differentiable at most places, just like most functions are continuous at most places. And it is going to be important to find out that a function is differentiable for it to be useful to us. So this is very abstract, so let's just look at an example. Let's take a function, say f of x equals x squared plus 2, which we kind of know is a function that looks sort of like this. It starts at 2, comes up like this. So, what are the things that we could find? Well, we could take from 1 to 4. And say we wanted to find this first thing, the average rate of change. That would be the slope of that line right there. So what would be the average rate of change from x equals 1 to x equals 4? I'll just call it the average rate of change, x equals 1 to x equals 4. We can find it from this formula. We're just going to find the slope of this line. So it's going to be f of 4, and what is this point going to be? 4 comma 16 plus 2 is 18, and at 1 you're going to be at the point 1 comma 3. So the rise over the run is, you're going from 3 to 18 and you're going from 1 to 4. So altogether you get 15 over 3, or 5. So on average, between this point and this point, the y value is going up by 5 for every 1 that the x value goes up by. Now, if I wanted to know, say, just the slope at point 4, what if I wanted to know this slope right here? I could use this formula right here. So I could say f prime of 4 is the limit as h approaches 0, and then I have to go f of 4 plus h. Well, this is f of x, so what's f of 4 plus h? 4 plus h squared plus 2. And then you'd have to go minus f of 4. f of 4 is 18 all over h. And then you'd have to do a little bit of algebra. So what do you get? 16 plus 2 is 18, and then you have minus 18. So the numbers are going to go away. When you square this out, you get 8h plus h squared. We're almost there. I can divide an h into each one of these terms, and I get 8 plus h. And then what's the limit as h approaches 0 of 8 plus h? It's just going to be 8. So the slope of this curve at this point is going to be 8, which in an actual application, when x and y really are representing some real-life variables, that rate of change is going to be something that might be very important. And the last formula that we haven't used is this one. What is f prime of x? What's the derivative or the slope at every point on this curve? Well, now we have to use this formula. So what is f of x plus h? Well, it would be x plus h squared plus 2 minus f of x, and f of x is x squared plus 2 Don't forget to put your parentheses all over h. Oops, I forgot. Right in here should be the limit as h approaches 0. So now I get, I won't forget it this time, the limit as h approaches 0. And now I can just square this out. X squared plus 2xh plus h squared plus 2 minus x squared minus 2. And it's looking pretty complicated, except this 2 cancels to the minus 2, and this x squared cancels with the minus x squared, and now h divides into each one of these terms, and I'm left with 2x plus h. And if I take the limit as h approaches 0, I just get 2x. So, a little bit of work, but we come up with a derivative function. This gives you the slope at every point x. And let's just try it out at x equals 4. What would be f prime of 4? 2 times 4 is 8, the same thing that we found here, which it should. And what is the slope right here? F prime of 1 would be 2. So you can see the slopes are getting bigger and bigger as you go up there. So anyway, we've made a lot of progress there. Now, just a couple other things. What if there is another formula that we can use if we only want to find the slope at one point? So say I have y equals f of x, and I have that same thing where I have a function y equals f of x like that, and I'd like to find the slope at this point a. This is a perfectly good way to do it right here, but there's going to be a reason why we might want to do it this other way, which you don't know right yet, but you'll see soon. So I could call any other point here on this line just the variable x. And what I'm really trying to do is find this slope right here. So what I could do, exact same idea as I did there. I'm going from this point here, which is a f of a, to the point x f of x. So the slope of this green dotted line would be the rise over the run. That's the rise, the change in the y value, and the run from here to here is x minus a. But we really don't want the slope of the green line, we want the slope of this red line. So the same idea, I'm going to keep bringing this point x closer and closer to a. And the way we do that is to take the limit as x approaches a. So this is just another formula that corresponds to this formula. That's another way of finding f prime of a. So let's just try it once on this same function right here. So what would we have? We would have f prime of 4 equal the limit as x approaches 4, and f of x is the function x squared plus 2, that's the f of x, minus f of a. Well, we know that f of a is 18 all over x minus 4. So, a little algebra, x squared plus 2 minus 18 is x squared minus 16, which factors into x minus 4 times x plus 4. And lo and behold, the x minus 4's cancel out. And then when we take the limit as x approaches 4, we get 4 plus 4, or 8. So we get the same answer. And that's what we would hope for. And I'll show you very soon why this formula is sometimes better than the other one. Because I know you're thinking one formula would satisfy us, but sometimes one is easier. This one was a little bit easier to do, but there's even going to be other reasons. So, let's end this video. What if we want to find an equation for a tangent line? So remember, a tangent line is just, anytime you have a curve, that's a tangent line, that's a tangent line. It's a line that has the same slope of the curve at that time. And the way we're going to find that is with the derivative. So say we had the function that's a little more complicated than a parabola like x squared plus 2 was. So say we have this function right here. I think you've seen enough detail that I'm just kind of showing you how much algebra you'd have to go through. If we want to know the slope at x equals 3, I could do it with either one of the two formulas for f prime of 3. Well, one of them is the first one we did, where this is f of a plus h minus f of a all over h. It's the same formula, you do it the same way. The algebra just gets to be harder, and that's why I don't want to lead you through step by step. I'm pretty sure I did that right, and I get negative 2/27. If I used this formula right here, which I probably should have boxed off because that's also going to be the third important formula that we learned, I can do it, the limit as x approaches 3 of f of x, which is now 1 over x squared, minus f of a. Well, 1 over 3 squared is 1 over 9 over x minus a. And again, I have to get a common denominator. I factor things out, and I get the same answer. And I guess my main motivation for showing you this problem is there's some incentive to try to come up with an easier way to find these derivatives because they're so important, but there's a lot of algebra. And 1 over x squared is not even a really complicated function. So now, if we actually wanted to find the tangent line, the last step would be to go, we could use the point slope formula. We know we've got the point 3, 1/9. And now we could say y minus 1/9 equals the slope times x minus 3. That would solve this problem. We actually found the equation of the tangent line, and if you graphed 1 over x squared, which looks something like this, what we just did was find the equation of that line right there. So I think we've covered quite a bit today. We're really getting into the heart of what calculus can do now. Right now, you're not so sure why these tangent lines are so valuable, but over the course of the year, you'll find that they're super valuable. So, thank you.